Okay, for the last part, homework 5, part C, we're going to be doing similar to part B of where we're calculating the extended reactions and the total molar flows of the system, but we'll be accounting for the water being returned, and we will be separating these three parts into their separate parts. So for the first thing we need to do, well, is how many equations and unknowns there can be. So to figure that out, there's going to be equations and unknowns for each of these different parts, the distillation, the two distillations, and the reactor. So firstly, we'll find how many equations we're working with. So for the reactor, there's going to be an equation for the mass balance of each component coming in. So we have 4 components and the mass balance for each of those. So 4 equations for that. And then also for the and that's that will be it for this reactor here. For the distillation, we'll also have another mass balance for the things going in and out of here. But because it is going to be separating in 2 different parts and returning the water, there's going to be equations for the vapor liquid equilibrium. So there will be another 4 equations for the distillation, which would mean a total of 8. And for our whole system thus far, 12 equations. And lastly, this distillation here will have another 4 equations for the mass balance. Then to calculate the number of unknowns we have, we will look at it and pretty much anywhere where something's going in or coming out, there's an unknown for the molar concentration of said thing and the flow rate. So there will be 4 unknowns for our alkene water. There will be 4 alkenes for what's going into the distillation tank. There will be 4 more coming out and going down. So we're up to 20 so far. There will be 4 unknowns leaving this distillation here, and we'll have 4 more unknowns for our ether and our alcohol, which is a total of 32. And there are 2 more we need to account for, which is our extent of reaction for reaction 1 and reaction 2, so plus 2, giving us a total of 34 unknowns and 16 equations. So now we'll move on to the next part. We'll start here from our homework 5 part B, and we have our stuff from our library. We imported NumPy, SciPy optimized root, JAX, and JNP for much later. And we're going to have our equations again, but eventually these will be converted to our dictionary. And these equations, some of them can stay the same, but we'll have to add d dot, d dot, d dot, d dot, products. This will be changed to our distillation feed multiplied by our distillation feed molar composition and our reactor feed forgetting the d dots here, will be our d dot water F times our d dot water Y, d dot alkene F times our d dot alkene Y. But now, since we're accounting for what's being recycled, we're going to have our D1D, D dot D1D multiplied by D dot D1DX plus our D dot AZ water times D dot AZ water X. That should give us everything we need for our reaction or reactor to start off with. what's up here? This doesn't need to be unpacked anymore. And then we can get our reactor balance. It's going to be equal to our feed plus reactions minus our products. Next, we can move on to our recycled water balance. So recycle balance will be equal to all of our waters coming in. So that will be our d dot water F plus d dot D1D plus d dot AC water, which will be divided by our alkene flow rate. So d dot alkene F, and to equal it out, we will have what we specify to be our how much more water is coming in than the alkene. So what did we call it? Oh, call it our water alkene ratio, WAR. Sure. And then next we can move on to our distillation, our D1 here. So firstly, we have what's going into that. So our D1 balance. So what's going in would be our D1F. Just copy this over quickly. And what's going out would be our D dot D1 B, and that would be multiplied our D dot D1 BY, and what's going out would be our D dot D1 X is here. So that should be our balance for our first distillation. And now we can move on to our AZ balance. So AZ balance will be equal to what's coming into our AZ, which would be this. And then what's going out, which would be our water that's getting recycled. And what's also going out would be our products, which is the isopropanol and diisopropyl ether. So what do we call that? So minus our d dot alcohol, and that would be multiplied by our alcohol X. And we'll also need to account for our d dot ether times our d dot ether X. So that should be all we need to in terms of our equations. And next we can move on to defining our unknowns and specifying some things. Before we move on, we need to get our equation for vapor-liquid equilibrium, vapor-liquid equilibrium, which would be equal to our D1 By divided by our D dot D1 By divided by D dot D1 Dx minus our D1K, because we want this to be equal to that, and when it resolves to the root, we just have to subtract it to make it equal 0. Then we can return what we want. So we will return, and we'll jnp.concatenate and we're gonna want our balance. We're going to want our D1 balance. We're going to want our D1 vapor liquid equilibrium and our AZ balance. And we also need our recycle balance here. Oh, shoot. I don't remember the syntax. Here we go. It's JNP dot at least 1D, and that will be of our recycle balance. Now we can move on to getting to specifying some of our variables. So we'll take these, set them down here for now. Should just be able to get rid of this. Okay, we can now move on to defining some of our variables and converting it into a dictionary. These need D dots in front of them. D dot, D dot. Okay. So now our E equals dot dict. And we'll just throw some E's in front of these ones we've already had, which will be the same for this problem as well. So our E dot return ratio will be equal to 12. We can then do our E dot D1F, which will be equal to a range, because we're not entirely sure what it'll be yet. And that will be, we'll call this, this will be our E dot war multiplied by our E dot alkene F. The lower limit is 0, and this, the upper limit, will be just 2 multiplied by that. Our E dot D1 Fx will be comp of 0.01, 0.03, 0.06, and 0.9. So that should mostly be next. We have our E dot D1V, which will be another range, which you can say it's the same thing. However, since it's going, say divided by 2, since it's going out the top and out the bottom, we can have our E dot D1VY equal to comp of 0.01, 0.23, 0.33. Next, we have our E dot D1D, which will be same thing here. Then our E dot D1 DX, which will be another comp. And we can say this one is very small amount of the alkene, maybe a little bit of these. The next thing we need, so we'll check, got all those. Now we just need what's going out of our AZ. So that will be our AZ water, our ether, and our alcohol. So E dot AZ water will be equal to, say the same thing here. That needs to be divided by 2. Our E dot AZ water X, this one, I believe, is the one that we're supposed to be defined here. So our AZ decanter mole fraction of this one will not be a comp, it will just be defined. Getting rid of some of the unknowns. And then we need our E dot ether, which will be equal to, we can say, our range and our alkene F divided by 2, 0, alkene F times that. Just needs the E here quick. All right. And then our E dot ether X will be equal to comp. Oh, never mind. These are defined already up here. So I'm just going to move these quickly. And then our E dot ether, or alcohol, instead alcohol. So this one should be a 4th. And another range. This will be very similar to this one, just divided by 2 instead. I don't know if I got the parentheses in there. Yep. So that should be our dictionary defined for everything we need. Oh, there's one more. It was our E dot D. I'll put it where it's supposed to be, around here. So E dot D1K is equal to 110.5.2. So that will be NV dot array of 110, 5, and 0.2. And I believe now we should be able to move on using our root solver. What doesn't it like? I reran this and it seems to be working, although I didn't change anything here, so I'm hoping that was the problem. So our x2 and t, our wrap, our x2 unknowns, and our constant is equal to our d2 and t of e. That works. And now we can get our wrapped q. EQs here is equal to wrap of our function. So EQ, see if that goes. All right. Our solution will be equal to our root solver of our wrapped equations, our x0, jax equals jax dot check of our wrapped EQs. Does that work? No. Why does that not work? Where's that at? No object has reaction extent. Oh, we need our E dot, our reaction extent. Our xn1. We can say this range of 50, 0, and E dot alkene F. Then we can have our E dot reaction 2. This one should be lower. 5. That's upper bound again. D dot reaction. So now, does this give us? Works. So now we can see our solves converges, get our unknowns. We just have to do our x2 unknowns of our solve function, and we just want the x values that and as and that returns us all of our unknown values. So our flow rates for D1F and our molar compositions. And looks pretty good, I'd say. Alrighty.